one more example at what we call zero launch angle. And again, that simply means that the initial velocity is all in the x direction. Next set of videos, we're going to do examples where the initial velocity is not in the x direction. But for now, we're going to stick with that. So this basically means, mathematically, zero launch angle means that V naught is V naught x. Okay, it's all in the x direction. So here's what we got, friends. We have a car going to make a jump across the river. There's the river, there's the car. And what we want to happen is this. The car is going to launch out into space. It's going to leave the cliff here. It's not really a cliff. It's 3 meters high, so it's 10 feet high. It's pretty far to fall on a car. But we want to make it, we want him to make the jump. So, or maybe it's Thelma and Louise and we want them to make the jump. But Thelma and Louise flew a lot further down than 3.0 meters. Do you even know what I'm talking about? Old movie. Anyway, Thelma and Louise drove a car off a cliff at the end of the movie. Very dramatic. Okay, lots of pathos. But it was a lot higher than 3 meters. The point is, anyhow, getting a bit of field here. The car goes off the little cliff here, and we want to know what must its velocity be when it leaves the cliff so that it makes the jump. If it goes too slow, right, it's going to right into the water. But if it goes a little faster, it'll go further before it hits the water. If it goes a little faster, it'll barely make it. And we want to know what speed is required so that it barely makes it. Follows that trajectory. There's that word again, trajectory. What we want to know is what initial velocity is required. We know it's in the x direction. So all we really need to do is find its magnitude. Okay. That's what we want to know. Such that it makes the trip. Well, here we go. We want to know its initial velocity. And we know that its initial, for zero launch angle, its initial velocity is the same as the initial x velocity. So let me actually write it this way. So what we're really looking for in a zero launch angle deal like this one is V naught x, because V naught and V naught x are the same. We want to know what V naught x is. Okay. So here we go. There are 3 V naught x's. Look around. Look up, down, look down, all around. There's 3. One there, and one there. Numbers 1 and 3 do not help us, because you can only solve those for V naught if you know the final velocity. We don't know the final velocity. We don't know the velocity when it gets down here. We don't know that. We could find it later, but we don't know it. So we're going to have to look at number 2 right here. Okay. But before we do that, the right step, and I should take things in steps here, is to write down the stuff that we know, right? Do we know what x naught is? Yes, it is 0. Because its initial point is right here when it leaves the cliff, and that's at x equals 0. Do we know the final x? Yes, we do. It is, no, we don't know it. We don't know the final x. Okay. Actually, we do. We do know it. It's right there, right in front of me. Let's see, 20 meters. Right there. The final position is 20 meters. It's going to move from 0 to 20 meters in the x direction. How about y naught? Do we know y naught? Yes, we do. It is 3.0 meters. It's initially 3.0 meters above the x-axis. Do we know the final value of y? Yes, we do. It is, say it out loud, let me hear it through the internet. 0, correct. Y ends up hitting, here's the axis, here's the x-axis, so it's going to end up at 0. Okay. Great. Do we know, let's see, V naught x? No, we don't. That's what we're looking for. Do we know V naught y? Yes, we do. It is 0, because again, at 0 launch angle, v naught y is 0. There's no y component to that vector. It's all in the x direction. It's perpendicular to the y-axis. Okay. We don't know time. We don't know time. Right? That's it. We don't know time. We could find time later on, but we don't need it. Okay. Just to be complete, we don't know what time is. But what we're looking for, the thing we seek is this. Okay, so let's look around. Like I said before, now we're getting, now that we've written down what we know, the stuff that we can know, now we take this junk and look at this stuff and we ask which one of these is going to be the most helpful to us. Well, this has got to be it right here. Because these two don't tell us anything. Like I said, these are not always that useful. V naught x is equal to final x velocity, but we don't know that. And actually this one and this one say the same thing, essentially say the same thing, almost identical. They don't really give us much. So we got to look at number 2. Let's look at number 2. X minus x naught is v naught x t. And there is the thing we're looking for. All right, x naught, we know, is 0. And this is the only way that we can find v naught x. This number 1 will not help us. Number 3 in the x direction will not help us, and none of the y's are going to help us with an x variable like v naught x. That's the only one that's going to help us. So we are forced to use this. V naught x equals x over t, which is like 20 over t. 20 meters over t. But, we don't know t. We got to find t to solve this problem. There's no other way to do it. No other way to do it. We have to find t. This is the only route to v naught x, the only one. You can try all day long. This is the only route to v naught x, but down that road carries you through time. We have to find the time. So we can't find time using any of the x information because we've exhausted the x information. Numbers 1 and 3 tell us nothing, and number 2, we've pushed it as far as we can go. So we've got to look to the y direction to find the time. So it's going to be either 1 or 2 because the time does not come into number 3. So we've got to use the y dimension to find the time. Remember, time is the same for x and y. It's the one bridge. It's the only bridge between the x equations and the y equations is the time. So we're going to find time using y. We can't use number 1 because we don't know vy. We don't know the final y velocity. We don't know it. So we can't use it. We've got to use number 2. Okay. And a lot of these things go away, right? Some zeros floating around over here. And they all, not all of them, but 2 of them show up in this formula. So let's find the time using the y formula. And then we'll take the time and stick it back in. This is one of those problems where in order to find the thing you're looking for, v naught x in this case, you've got to find another quantity, t in this case. So let's use this equation here. Okay, y equals y naught plus v naught y, there's our time, minus 1/2 g t squared. Okay, now let's go through and figure out which ones are 0. In the case of the x equation, only one of them was, but here, 2 of them are. Final y is 0, so this term is going to be 0. V naught y is 0, so that term also disappears, vanishes into thin air. So we're left with 0 equals y naught minus 1/2 g t squared. If we add 1/2 gt squared to both sides, 1/2 g t squared equals y naught, and solve this for time. This is similar to the time that we solved in the baseball problem. If you go back and look at the math, it's exactly the same. So time, I mean the square, I skipped 1 or 2 steps in algebra here. 2 y naught over g. Square root of 2. Y naught we know. Boom, 3.0 meters. G we know, 9.81 meters per second squared. So T, 0.782 seconds. That's how long it takes the car to sail off the cliff and then hit the edge of the land here. Okay. So now we know the time, and we can take that time, put it in right there, and solve for V naught x. Okay. So let me do that up here. V naught x is 20 meters over the time, which we have just found using the y information, 0.782 seconds, which comes out to about 26 meters per second. Slightly less, I got 25.575 rounded up to 26. 26 meters per second. That is the answer. V naught must be 26 meters per second. 26 meters per second. For those of you who wonder how fast that really is, that's about 60 miles an hour. Okay, so it's a realistic speed. That's how fast you got to drive the car off the cliff to get it to land on the corner, barely. If you go any faster than that, it's still cool. You'll make it further out. Okay, but any slower than that, and boom, you're sleeping with the fishes, as they say. Okay. I would love to ask you, I'd love to be in a classroom with you now, like a live classroom, and say, are there any questions? I would like that. But I can't. That's it for this lecture, this video. Next up, we'll talk about launch angles that are not 0. We're still in projectile motion, still in chapter 4, still going to be using these equations. Okay, we're not really going to be leaving these equations for the rest of the whole chapter. This is basically the show. This is basically the show for chapter 4. With the exception of a little bit of stuff at the beginning, we'll talk about that turtle and the eagle. This is the meat of chapter 4 right there. See you next time when we'll go to a non-zero launch angle.